The fundamental theorem of calculus. This is the theorem that bridges the ideas between the differential calculus and integral calculus. Our objectives is to understand both parts of the fundamental theorem of calculus, part 1 and part 2. We're going to differentiate functions using properties of integrals. And lastly, we're going to evaluate definite integrals using this new fundamental theorem of calculus. We'll begin with a definition. Let f of t be a continuous function for t greater than or equal to a. The cumulative distribution function for f of t with left endpoint a is this g of x function defined in the form of an integral where x is greater than or equal to a. Notice the independent variable is x. In the form of the integral, the x is right there. The cumulative distribution function accumulates a number for the region bounded by the graph of f and the t-axis on the interval. Geometrically, this looks like shaded regions, but you really are just accumulating a number from left to right. The number could be negative or positive. Why don't we look at a picture and an example to dive into some more details. Note that g of x is represented by this interval from -1 to x, where x is actually a number between -1 and 9. So what is g of -1? Well, according to your properties of integrals, we could write g of -1 is equal to the integral from -1 to -1 of f of t dt, which we know is 0. Is g of 0 positive or is g of 0 negative? Where is g of 0? We're going to go ahead and shade it from -1 all the way up to 0. It's right there. It's this accumulation below the x-axis. So that accumulation is negative. What is g of 3? Once again, we're going to accumulate a number below the x-axis and between the function. So g of 3 starts from -1 all the way up to 3, and you have to shade between the x-axis and the function. Notice it is accumulating a negative quantity from left to right. And even tells you what that quantity is. It's actually -27. What is g of 5? G of 5 is accumulating -27, and accumulating here means add. We have -24. G of 5 is -24. Is g of 8 positive or is g of 8 negative? So remember, g of 8 starts with a shaded region between the x-axis and the function, starting at -1, and we keep shading from left to right all the way to 8. Looks like it's accumulating more negative than positive, so we know that g of 8 is actually negative. What is g of 9 minus g of 3? To look for g of 9, g of 9 is an accumulation. We first accumulate negative 27, then we accumulate 3, and then we accumulate negative 35. Simplifying that, we get negative 59. Now what is g of 3? G of 3 is negative 27. We want to find a difference. G of 9 minus g of 3 we get negative 32. What is g of 9? Let's go back and accumulate from left to right, starting with negative 1. And we have to shade all the way up to 9. Accumulate here means to add. So the expression g of 9 is simply going to be negative 59. What is g of 5 minus g of 3? From part D, we know that g of 5 is negative 24. From the graph, g of 3 is equal to negative 27. So g of 5 minus g of 3 is going to be positive 3. Let's observe a different example where we define the accumulation function from this continuous function f of t equals 2t plus 3. We'll define the continuous accumulation function on the interval 2 to x. The idea here is we want to find the area underneath this linear function bounded by the t-axis. Notice it is the shape of a trapezoid. It's just tilted. Here is a base. Here's another base. Why don't we find the area of this trapezoid using the area of a trapezoid formula? Substituting everything, we know that this base here has the length f of 2, which is 7. We know that this length here is going to be f of x, which is 2x plus 3. Why don't we simplify g of x now? And notice g of x here is a quadratic. So we have g of x is accumulated, and it's a function of x. Now what happens when you take the derivative of this g of x? You simply get 2x plus 3. But we know what 2x plus 3 is. That's another name for f of x. Remember, we were given the function, the continuous function, 2t plus 3. So using the change of variables here, we can see that the derivative of the accumulation function gets back the original function, which leads us to the fundamental theorem of calculus. The Fundamental Theorem of Calculus, Part 1. This fundamental theorem bridges the ideas from differential calculus to integral calculus. Let's begin. If f of x is continuous on a closed interval a to b, then the cumulative distribution function g of x, defined by this integral, for the interval a to b with x in between it, is continuous on the closed interval ab and differentiable on the open interval ab, and the derivative of g of x is equal to f of x. This actually expresses an antiderivative of f of x in terms of an integral. Important notes about part 1. G of x is always read as a function of x. Note that the variable x is at the top of the elongated s, and it must be at the top. T here is just acting as a dummy variable or a placeholder to allow you to finish processes. An antiderivative of f of x is g of x. This is because the derivative of g of x gets you f of x. Once again, the derivative of g of x gets you f of x. In the proof, it is enough to show that g of x is differentiable because differentiability implies continuity. Specifically, we'll show that the derivative of g of x is equal to f of x using the limit definition of a derivative. This proof uses many ideas that you have to grasp from differential calculus. The limit definition of the derivative, the extreme value theorem for a continuous function on a closed interval, properties of integrals, change of variables, and the squeeze theorem. Let's do a quick walkthrough of the proof. We're going to try to show that g of x is differentiable by using the definition of the derivative. Suppose f of x is continuous on a closed interval a to b. Let x and x plus h be x values b in that open interval ab, with h greater than 0. Using properties of integrals, we'll go ahead and observe the difference quotient. One property that you want to have mastered is this one. This looks like the cut and paste property of integrals, where you're simply splitting up the domain. This property is being used. You could see it right here. It's being used for this integral here. Notice we're going to subtract from the first term this term, and those actually become 0, and now the difference quotient looks like this. It's actually a definite integral for the continuous function f of x. By the extreme value theorem, we know that f of x is continuous on a closed interval a to b. That means there is a u or v, I should say, there is a u and v in this closed interval x to x plus h, such that f of u equals m and f of v equals uppercase m. The uppercase m resembles a maximum, the lowercase m resembles a minimum. Thus, we could find a lower bound for this integral. We could just take that minimum value and multiply by the width of this interval. Here's the minimum value, multiply the width of this interval, which is that. The upper bound for this integral will be the maximum times the width of that interval. Notice this simplifies very nicely. We have h over h, which is 1. Over here we have h over h, which is 1. And now we have the difference quotient is in between f of u and f of v. Now we're going to perform a change of variables here. We're going to perform a change in variables. Remember, we have an x number line. And that number line goes from x to x plus h. As h approaches 0, what happens to this interval? This interval will have to get smaller and smaller. But remember, there's actually a u in there and a v in there. So somewhere along the interval here, we have a u and v. So as h goes to 0, what happens to v? So as the interval is getting smaller, v is going to be pushed towards x. As h gets even smaller, what happens to u? U will also have to be pushed towards x. So we have u being pushed towards x, and we have v being pushed towards x. Since f of x is continuous on a closed interval a to b, we'll use the change of variables and analyze these limits. Notice u is the variable here, and this expression, v is the variable here. Since f is continuous, we know that both these expressions have to equal f of x. This brings us back to the inequality. Take this inequality, and we're going to observe limits where h is approaching 0. But h approaching 0 is equivalent to saying u is approaching x and v is approaching x for these specific functions. Now we have the difference quotient of g with the limit as h approaches 0 is being squeezed between f of x and f of x. As a result of the squeeze theorem, the derivative of g exists, and we have the derivative of g between f of x and f of x. Thus, the derivative of g of x must equal f of x.